Let's start working stress method for rectangular section. There are a few assumptions. First of all, we have to know assumption, and to understand the subject RCC structure, first of all we have to gather some basic knowledge about working stress method. The analysis of reinforced concrete members subjected to bending are based on the following assumptions. First assumption is plane section of the beam before bending remains plane after bending. Second assumption is E, modulus of elasticity for the material is constant for tension and compression. Number 3, each layer is free to expand of contract independent. Number 4, radius of curvature is large at bending compared to dimension of cross section. In this figure you can see this is a cross section of a rectangular beam section. In the middle of this section you can see a dotted line, that is called neutral axis. Neutral axis for a beam section is the line of intersection of the neutral layer with the beam section. This is a straight line dividing the cross section into a tension and a compression zone. One of the basic assumptions made in the analysis of reinforced concrete beam is that the tension borne completely by steel. The upper portion of neutral axis is considered as compression zone and lower portion of neutral axis is considered as tension zone. That's why reinforcement is given in the lower portion. As you can see the cross section and stress diagram of rectangular section. In this figure 1 you can see the cross section of the beam. Overall depth, that means top fiber to bottom fiber, the total depth is denoted by capital D. Approx at the middle of this section there is a dotted line. As I told earlier, this is the line which is called neutral axis. The upper portion of this line is called compression zone, lower portion of this line is called tension zone. You can see 3 circles in lower portion. These circles are cross section of reinforcement bar. As I told earlier, tension is completely taken by steel reinforcement bar as per assumption. That's why in tension zone reinforcement is necessary. In upper portion also reinforcement given, but mainly to make the mesh. From top fiber to neutral axis is the depth of neutral axis. In case of working stress method, this is denoted by small n. You can see the abbreviation C suffix C, that means clear cover, which is from the lower end of the bar to the bottom fiber of this cross section. Now C suffix E, that is effective cover, that means from bottom fiber of the cross section of the beam to middle of the bar, that is called effective cover. Now in stress diagram you can see in upper portion one abbreviation written, that is sigma CBC, and in lower portion up to the effective cover, that is sigma ST. Sigma CBC means permissible compressive stress in concrete and sigma ST means permissible tensile stress in steel in working stress method. Now, from the top fiber to the effective cover, this length is called, actually this depth is called effective depth of the section. Few more basic concepts and terminologies before starting design. Now the term, you can see, moment of resistance. Actually, we know that when load applied, a moment comes to the structure. To resist the moment, we have to design the structure. So, main purpose of design is to resist the moment. That means the amount of moment come to the structure, we have to resist that much moment. So, the moment of resistance is the algebraic sum of moment about neutral axis offered by the internal forces due to bending moment is called moment of resistance. So, as per the concept, the value of moment and value of moment of resistance are equal. Now, next terminology is balanced or economic section. Actually, depends upon the amount of reinforcement, amount of steel. There are two main different type of section: balanced section and unbalanced section. In practical case, balanced section is not be designed, it cannot be designed actually, but balanced section is our reference, is our benchmark to understand. So let's focus on balanced section. This is a section in which the quantity of steel provided is such that when the most distant concrete fiber in the compression zone reaches the allowable stress in compression, the tensile stress in the reinforcement reaches its allowable stress. For example, let the allowable stress in concrete and steel be 7 Newton per millimeter square and 1. Hence, for the balanced section, when the extreme stress in concrete reaches 7 Newton per millimeter square, the stress in the steel will be 140 Newton per millimeter square. That means the maximum stresses, maximum permissible stresses reaches in compression zone and tension zone at the same time. That is called balanced section. The position of neutral axis with this condition is called critical neutral axis, which is denoted by small n suffix c in case of WSM. There is another term, that is actual neutral axis. That means in case of unbalanced section, the actual position of neutral axis, that is called actual neutral axis. In case of balanced section, actual neutral axis and critical neutral axis is equal, is in same position. The neutral axis corresponding to this condition is called critical neutral axis, as I say earlier. So we can see Na is equals to Nc. Now, unbalanced section. There are two types of unbalanced section: under reinforced section, over reinforced section. Now, under reinforced section, this is the section in which the quantity of steel provided is less than what is required for a balanced section. In this case, when the stress of steel reaches its permissible value, the corresponding extreme compressive stress reached in concrete will be less than the permissible value. For example, taking the permissible stress in concrete and steel as 7 Newton per millimeter square and 230 Newton per millimeter square, like earlier, respectively. Now, we find that when the stress in steel reaches 230 Newton per millimeter square, the extreme compressive stress in concrete will be less than 7 Newton per millimeter square. So, in this case, actual neutral axis is less than critical neutral axis. That means if we consider from top fiber, the position of neutral axis line is slightly upper than the position. Next is over reinforced section. This is a section in which the quantity of steel provided is more than what is required for balance section. In this case, when the extreme compressive stress in concrete reaches its permissible value, the corresponding tensile stress in steel will be less than its permissible value. Again, for example, taking the permissible stress in concrete and steel as 7 Newton per millimeter square and 230 Newton per millimeter square respectively. Now we find that when the stress in concrete reaches 7 Newton per millimeter square, the extreme tensile stress in steel will be less than 230 Newton per millimeter square. That means actual neutral axis in this case is greater than critical neutral axis. Now in case of cross section of the rectangular section, from top fiber, the position of actual neutral axis is more deeper than critical neutral axis. Yeah, I think this is clear. Now the next term is lever arm. Lever arm, actually this is the distance between the line of action of the resultant compression and the line of action of the resultant tension. The line of action of the resultant compression is at the level of centroid of the compressive stress diagram, that is at the depth of 1/3 of depth of neutral axis, that is n/3 from the compression edge, that means top edge, but the resultant tension is at the level of reinforcement since the tensile. So these are the basic terminologies, the basic concept of working stress method as well as RCC structure. That's all for this lecture. Thank you.